A San Francisco company is selling a box that makes drinking water out of nothing but air, enough of it to run an entire house, with no pipe to the street and no well in the ground. Aquaria Technologies builds an atmospheric water generator about the size of a large appliance. It draws in ambient air, condenses the moisture into liquid, then filters and sterilizes it past federal drinking standards. A single unit makes up to 132 gallons a day. Pair two of them, and you can cover a whole household's supply. If it works as promised, it hands a home something it has never really had, which is ownership of its own water, free of the utility, the well, and the contamination risk that comes with both. We are going to trace the air through one of these machines, find the point where the physics pushes back, and work out whether water from thin air is ready for an ordinary home. Almost every home in America rents its water. You pull it from a municipal main or a private well, and in both cases, the supply is something you depend on but do not control. Those systems are under more strain than most people realize. American drinking water infrastructure was graded a C- by civil engineers in 2025, with frequent main breaks, pressure drops, and boil water notices. As easy groundwater runs short, utilities are pushed toward costlier sources, and those costs land on your bill. Then there is what is in the water. A 2023 US Geological Survey study estimated that at least 45% of US tap water carries one or more PFAS, the so-called forever chemicals. The EPA finalized its first national limit on them in April 2024, capping two of the worst at 4 parts per trillion. Private wells are exposed too, and they sit outside federal monitoring entirely. So the supply is aging, the costs are rising, and the quality is uncertain. Owning your own water, made on site and clean to a known standard, is exactly the problem Aquaria set out to solve. The company was founded in 2021 by brothers Brian and Eric Sheng and runs as a San Francisco B Corp. Brian wrote his Princeton thesis on water and energy infrastructure. The idea behind the product is one you have already seen on a cold drink can on a summer day when beads of water form on the outside of the glass. That is condensation. And the machine does it on purpose, at scale. Here is how the Hydropack works. A fan pulls humid outside air in through a pre-filter, then drives it across a coil chilled by a refrigerant. When the air drops below its dew point, the vapor it carries turns to liquid and beads on the metal fins. That raw condensate drips into a collection basin, which is only the start. From there, the water runs through a treatment train. Ultrafiltration membranes and activated carbon strip out particulates, organic compounds, and heavy metals. Because still water can grow bacteria, a UV lamp disinfects the tank every few hours while it waits. Independent labs testing the output found non-detectable levels across more than 50 contaminants, including lead, arsenic, nitrates, PFAS, and microplastics. The result is water with no pipe and no aquifer behind it, monitored and scheduled through a phone app. And that app is doing more than tracking gallons. You can set the machine to run during the day, when rooftop solar is generating, and during the more humid hours, when pulling water from the air takes less work. Your water, in other words, is timed to your cheapest, easiest conditions. A single Hydropack makes up to 132 gallons a day, at about 0.93 kilowatt hours per gallon. The Hydropack X pairs 2 units and reaches up to 264 gallons, enough to take an average household off municipal water completely. That capability invites an obvious question, which is how the cost stacks up against the tap you already have. Honestly, against cheap city water, it does not. At an average US electricity rate, the Hydropack's power draw works out to around 13 cents a gallon. A municipal utility delivers water for a fraction of a cent. Measured purely as a way to make standard tap water cheaper, an atmospheric generator loses, and it loses by a wide margin. But that comparison only holds where reliable, cheap, clean water already exists. Plenty of places do not have that. Extending a municipal line to a rural property or drilling a deep well can run past $50,000, with no guarantee the water you hit is safe to drink. Set against that, a machine that makes its own supply starts to look reasonable. And the running cost is not fixed. Because the unit can be scheduled onto daytime rooftop solar, the electricity behind each gallon can fall toward nothing. Pair the Hydropack with panels and a battery, and the 13-cent figure is a ceiling, not a floor. There is also a cheaper, cruder rival worth naming, which is bottled water. It runs anywhere from 50 cents to $2 a gallon, comes wrapped in plastic, and carries the embedded cost of manufacturing and trucking every bottle to your door. On price per gallon for clean drinking water, the Hydropack beats it comfortably. The case for making your own water is sharpening because the pressures behind it are all climbing at once. Drought is the loudest of them. Severe dry conditions now stress surface reservoirs and shallow wells across large parts of the country, and as water tables fall, homeowners are forced to drill deeper at rising cost, often finding water heavy with arsenic or nitrates. The contamination story is moving fast too. With the EPA's 2024 PFAS limits now in force, utilities face an estimated $1.5 billion a year in compliance costs to strip those chemicals out, and that bill flows downstream to ratepayers. A machine that sidesteps the ground and the pipes sidesteps that contamination at the same time. The third shift is the one that makes the economics work, which is solar. Rooftop panels and home batteries have become common enough that pairing a water generator with them is no longer exotic. Cheap daytime electricity is exactly what an energy-hungry process like this needs, and it is increasingly sitting right there on the roof. For all that promise, this technology has real ground to cover, and the first obstacle is built into the physics. Pulling water from air is energy-intensive in a way that is hard to escape. Condensation means cooling a whole stream of gas below its dew point, and the water molecules in that gas are thinly spread. By some measures, the process costs many times the energy of desalinating seawater for the same amount of water. Solar pairing softens the bill, but the underlying hunger of the method is a ceiling on how cheap it can ever get. What would lift that ceiling is a move away from refrigeration entirely toward advanced desiccant materials that grab and release vapor using low ambient heat. The second limit is the weather itself. These units rely on the moisture in the air, so they need it warm and reasonably humid, performing best above about 59 degrees Fahrenheit and 30% relative humidity. In a cold snap or a genuinely arid place, output can fall by more than 80%, which makes the machine an unreliable sole source in those conditions. Aquaria's own answer is honest about this, recommending a storage tank to bank water during good spells and a second source, like a well or delivery, for dry months. The fix at scale is smart software that schedules generation for the most humid, sunniest hours and rides out the rest on stored supply. The third challenge is history, because someone has tried selling water from air before and stumbled badly. Source Global, formerly Zero Mass Water, raised $270 million for solar hydro panels, then ran into high failure rates and thin real-world output. Its panels produced only a couple of quarts a day in practice, pushing the effective cost of that water far above the global average for tap. The lesson sits over the whole category. Winning means industrial-grade reliability, real warranties, and a maintenance network, none of which is proven until the field data is in. And then there is the price. A whole home Hydropack runs roughly $14,000 to $35,000 for the unit, plus $10,000 to $25,000 to install. Even with those caveats, the momentum behind Aquaria is real, and the money is following. The company has raised $112 million, including a $100 million project financing facility built specifically to take the upfront cost off the customer. The plan borrows from the residential solar playbook, letting homeowners pay the hardware off over time rather than facing the full sticker price on day one. The headline deployment is in Hawaii, where Aquaria is working with a developer on a planned community of around 1,000 homes supplied on atmospheric water alone. Rural Hawaiian projects often stall for lack of municipal water and the steep cost of drilling, and pairing the generators with rooftop solar and batteries is meant to decouple the whole development from that bottleneck. The company has also partnered with Stanford's Atmospheric Sciences program to tune the efficiency of solar-powered capture. So are these commercially available? The short answer is yes. You can buy one from Aquaria directly, as long as your climate allows and you are willing to pay the premium. In general, the wait for the mass market deployment is less about availability and more about the price falling and the field record building as the technology scales. So the question this leaves you with is not really about the engineering, which works. It is about what your water is worth to you. In a place with cheap, clean, reliable tap water, the math does not favor this machine, and probably will not for years. But that is not where most of the pressure is. The harder call belongs to the household at the end of a failing line, on a well turning up PFAS, or watching the bill climb every spring. For them, it comes down to a straight trade. Keep renting a supply you do not control and cannot fully trust, or pay a steep price once to own the thing outright, betting on warm, humid air and a sunny roof to carry the cost down over time. Cheaper water you depend on, or dearer water that is finally yours. Which one is worth more depends entirely on how reliable the tap behind you really is.